Hello everyone, this video is prepared for a deep learning course in 2020, and here our team will tell you about our project UnDeepVO, unsupervised deep visual odometry and depth prediction. Our team consists of Alexey Kashap, Anastasia Kishkum, Dinar Sharfudinov, Mikhail Kurenkov, and Valera Ilyin. One of the areas of robotics which attracts the attention of researchers is autonomous vehicles. However, self-driving cars still haven't appeared because the developers face many issues. One of the main problems is to build a perception system. There are three main key components of robotic perception: depth estimation for collision detection, visual odometry for ego motion estimation, and SLAM for robot localization. All these algorithms can be deep and simultaneous. Deep learning approach is applicable also because there are three main challenges in the robotics perception system. Robots use sensors like LiDAR, which are very expensive, fragile, and consume a lot of energy. The second issue is that the operation environment is complex and dynamic. And the last issue is different environment condition. For example, different line condition, day, night, rain, and smoke. To overcome these issues, we need to use cheap RGB sensors, apply deep learning algorithms, and use an unsupervised approach. Thus, our goal is to create unsupervised deep depth estimation and visual odometry algorithms. Methods for depth estimation can be divided into main groups: supervised and unsupervised approaches. We focus on unsupervised methods, which don't use ground truth data. Unsupervised or semi-supervised algorithms often use a photometric consistency loss between images for depth reconstruction. For this purpose, these methods have as input either monocular video sequence or stereo pair images. The methods which use stereo images are based on a left-right special photometric consistency loss, as first described in the article monodepth 1. And temporal photometric consistency loss usually is applied in methods that are based on prediction of depth and visual odometry from video sequences. One of the first such methods is described in the article about SFM learner. The combination of this approach is presented in the work UnDeepVO. During the last 3 years, several enhancements of supervised and semi-supervised methods are presented. For example, in the article monodepth 2, after describing the following improvements: we use minimum instead of average for photometric consistency loss to remove outlier pixels. Also, researchers apply a mask for removing occlusion regions and utilize different scales for depth prediction. Also, many approaches come into existence which is based on adversarial learning and GANs.
So our overall solution consists of two parts. First one is a unit like DepthNet architecture, which is encoder-decoder model. We had 6 blocks in encoder and as well in decoder part. And that network allows us to predict depth in each pixel of the images. The second part is a POSNet network, which is VGG-like. This network allows us to predict translation and rotation. These two networks work together in that way that at each step we have 4 images. For each image we predict depth, and also we predict transformation between consecutive images. Then we use all that parts for calculation of losses, about which we will explain you later. So that was our basic model. Here we decided to improve our model, and the first and like the most important part is using pre-trained ResNet 18 as an encoder part in both networks. Using transfer learning approach allow us to improve the result of our network. And the idea here is that pre-trained weights already have a lot of information about the different objects and shapes on the images. The second thing is LO activations, which work well in this kind of task because of faster conversions and better results of the networks. Next thing is reflection paddings that decrease amount of artifacts on the borders of the images. Also, it's important to notice that we were feeding pairs of images into POSNet, and that required us to slightly change architectures of networks. And the last part we used weights on parts of the losses, so that the most important part has highest weight. All that improvements allowed us to get final model and good results.
Our network is trained in an unsupervised manner. It was said before that during a single iteration, the network predicts 4 depth maps. The prediction is done for 2 sequential frames of left camera and 2 sequential frames of right camera. If we know the intrinsic matrices of 2 cameras, the relative transformation between them, we can synthesize the right image from the left and the left from the right. Moreover, the quality of generated images highly depends on predicted depth maps. Therefore, by minimizing the difference between synthesized and real images, the network learns how to make more accurate depth prediction. This loss called photometric consistency loss. The next loss function, temporal photometric consistency loss. This loss uses the same idea, but for image sequences. We synthesize the next frame from the current for the left and right cameras as well. Then this loss function tries to minimize the difference between real frames and generated. The third loss function is based on the predicted pose. PoseNet predicts 2 poses for left and right images, and then the pose consistency loss minimizes their difference because the robot must have only one true position. The last loss function is inverse depth smoothness loss. This loss makes the predicted depth map more smooth. In the end, we sum up all loss functions according to weights adopted for our problem.
To train the model, we used Kitty odometry dataset. This data was collected by sensors mounted on a vehicle driving in a city landscape. 2 cameras are mounted on the same height and have the same rotation angle. To speed up our experiments, we trained the network only on the 8th Kitty odometry sequence, due to each sequence have about 8 gigabytes of raw images. It contains left and right color images, both cameras' calibration matrices, and ground truth trajectories. While training, we investigate step between images to make images more different from each other. To evaluate our model, we used a benchmark Kitty depth completion and prediction evaluation dataset. We used a validation part of this dataset that contains RGB images, camera parameters, and ground truth depth. Preprocessing step also has some specific features. We needed to process 4 related images in the same way. Also, we proportionally resized and cropped images for correct model input. Thus, our starting dataset was resized and cropped to 384 by 128 pixels, saving the image scale. It was also important to keep correct intrinsic matrices and rescale them respectively. Also, as described in the original paper, we applied different kinds of image color augmentation methods, such as brightness contrast, random gamma, and channel shuffling. Also, we applied random horizontal flip. To apply this kind of augmentation, we used an augmentation framework. The most difficult part for us was applying the same augmentation to 4 images simultaneously. For efficiency work, we used the MLflow instrument that provides an online storage for save our experiments. MLflow can store all information about a training process, including training hyperparameters, values of each loss, function, text, and generated images. The main power of this instrument is that all coworkers can look at the same results of every colleague and store all experiments from all devices and even from all collabs to one online dashboard. To deploy this instrument, we rent a small server. Thus, we aggregate more than 400 meaningful experiments and can clearly see how each hyperparameter influences the final result. Our work was well organized, and we efficiently used GitHub possibilities such as project, issues, tasks related to commits, and work style Git flow with code review. Such style of work fetches us to the stable package that can be installed by just one line. And all our experiments can be easily reproduced by several lines of code that you can find in our notebook or launch script in GitHub. Also, we use TensorBoard for short experiments and efficiently used GRS with parallelization to speed up the training process.
Initially, it was very difficult to launch a realized neural network successfully. Good results was so far from the real good results. The developed software components needed deep debugging. We tried to understand the root of the problem. For this, we generated a big amount of experiments. In the slide, you can see most significant generated solutions. So after a long time of debugging, we discovered and fixed next problems. One of the options to solve bugs is to generate image with generated depth map and image from one camera. Finally, you can see the results of our model related to depth visualization. As you can see, the image clearly shows the outlines of cars and pillars, and the last image shows a tree contour very clearly. We also evaluated our model based on the presented metrics. The evaluation was performed on the Kitty dataset for evaluating metrics.
We also compared results from our POSNet with other methods. VisNet generates visual odometry which can be integrated to vehicle position. We tested our method on Kitty odometry dataset, sequence 8. The graphic of ground truth data and our reconstruction is presented there. Our implementation has 11% of translation error and 4.63 for rotation error. This result is better than geometric method like ORGSAM, but worse than original method of UnDeepVO. The reason is that original implementation is trained on all 8 sequences, but we trained only on 8 sequences.
To experiment, we evaluate the trained model on images downloaded from the internet. We divided the downloaded images into 2 categories. The first part is the city landscape with roads, cars, buildings, pedestrians, and trees. The second category contains images that highly differ from the dataset. The results are presented on the slide. The left image shows the picture from the first category and looks similar to the images from the dataset. From the predicted depth map, we can easily distinguish a pedestrian, car, and also bicycle. Also, the network predicted a tight column on the left side, which is quite impressive. The center picture is also from the first category. In that case, the network could distinguish cars and walls of buildings. Also, we can see the different distances between cars, which look correct. The last experiment was done with a completely different image. We used the picture of a cat. It seems that the network interpreted the cat fur pattern as trees and didn't recognize the cat at all. As it was expected, the prediction is not correct. We also made a short video on Moscow streets and made a depth prediction via the network. This video is quite challenging for the model, as the height of the camera is particularly lower than in the dataset. Also, the video was recorded on the walking road, which is different from the road. And the last issue is that the dataset doesn't have grass at all, only shrubs. So we made the conclusion that to increase the result of your network, you should train on more different data.